Hello everybody, and welcome back to Ask Math Anything. Good evening from Pittsburgh, Pennsylvania, which is usually where we stream from here. If you haven't been here before, the way this works is that people come into the chat and they just start asking any questions that they want. Most of the questions are about math, and most of the questions are at levels that are around what we can talk about. But this is really just an opportunity for you to try to ask questions that you'd like someone to answer. And my job is to try to figure out if I can give you a lesson right on the spot. Now, I will prefer to choose questions that might be closer to the level of algebra or geometry that people who do middle school math competitions might be working on. However, I'm open to looking at what else there is. Maybe I'll give you a comment or two just to point you in the right direction. And if you haven't been here before, I want to let you know, I actually haven't looked at any of these questions beforehand. This is entirely unscripted. And what that means is that there might be mistakes. And so I need you, all of you in the comments, to go and help me to make sure that there aren't any mistakes. So what are the questions for tonight? Feel free to ask anything that you want. I'm going to go scroll a little bit in the chat so that I can also see what's going on here. Oh, interesting. I see one already from Alpha Ice. Now, that's an interesting question you've just asked because you have a key number in there that's related to something about this birthday problem. So the question is, what is the smallest number of people you would need to have in a room if you wanted to be certain that at least 25 of them have the same birth month? If you haven't been here before, you're now going to see me put on the blackboard. So let me write down the question so that we can all be thinking about it at the same time, right? The question is something like, how many people needed to guarantee that at least 25 have the same birth month? Now, if we lived in a world or a universe where there was only 1 month, that would be easy, just 25 people. But that's how you can start thinking about this. You see, suppose that we lived in a world where there are 12 months. Well, what's the worst case? For the answer for this, just think about what the worst case would look like. The worst case would be that there are 11 months where you're not quite past the 25. So 11 months with 24 people each. And then finally you have this one more month which is with 25 people. Actually, when I say that's the worst case, let me even say the worst case where I don't even have it. So let me adjust this. Let me say the worst case where I don't have at least 25 people with the same birth month. Let me be more specific what I want to do here, and also change one of the words in here too. Let me actually write it again nicely. That'll be better. What's the worst case? Oops, let's get a pen. What's the worst case with no months that have at least 25 people? Well, what that looks like is 12 months, and each of them has 24 people. 12 months, each with 24 people. Now, we're supposed to find out a number, how many people are needed to guarantee something. And what this says is that if there are 12 times 24 people, that's not enough to guarantee because it could look like this. And if it looked like this, no month has at least 25 people. So let's do the arithmetic now. I need to do 12 times 24. Oh, I want to do it in a way that's a little bit more fun. I know I could just write the 2, 4 and the 1, 2 and do a standard multiplication, but I sort of just like to do things different ways just because. Because usually you end up finding out some neat math while you're doing so. And when I see 12 and 24, the way I think of this is that 24, that's 12 times 2. So this is equal to 12 times 12 times 2. Now here's a useful trick when you're trying to do arithmetic accurately. I actually learned my multiplication table up to like 1 times 1, 2 times 2, 1 times 7. These are all easy. Like 7 times 6. And it went all the way up to 12 times 12. That's where I learned up to. So I happen to know that 12 times 12 is just 144. That's just burned into my head somewhere. Well, not literally, but somehow it's in there, right? So 12 times 12 I know is 144. And the reason I like to do this is because multiplying by 2 is relatively easy to do. You just kind of double every digit, and it works especially well if there's no carrying. So this 144 times 2 is 288. And what this means is that if I had 288 people, that's not enough to guarantee. So 288 people are not enough to guarantee. Guarantee what? Well, it's guaranteeing that there's some month with at least 25 people. However, if I just take one more person, that's the straw that breaks the camel's back. And what that means is if I just put one more person, actually then there's no way to have all of the months be less than or equal to 24 people. This was the maximum. We filled them all up. With one more person, you tick over. And with one more person, you tick over. And once you have ticked over, then there's got to be some months with at least 25. But one more, 289 people, will guarantee. Because at that point, it's just not possible that with 289 people, they all happen to have all the months with less than or equal to 24. So the answer to the question is this 289. Now, I also wanted to bring attention to this problem for another reason. It's because there's a classic problem that people often talk about in a probability class, which is that usually, not usually, but probably with high probability, about 50% probability, if you go and find 25 random people, it turns out that the probability that 2 of them have the same birthday, meaning like, I don't know, June 18th or something, the same birthday, the probability that 2 of them have the same birthday becomes close to 50-50. And that's why if you go into one of your classrooms and just be like, hey everyone, what's your birthday? About 50-50 chance. Like it's pretty balanced. About half chance, there's a chance that 2 of you are going to have the same birthday. And that's an interesting fact from probability. So when I saw this question, at first I saw 25, and I thought that's what you were trying to get at. But then I saw this instead, and I saw that you were asking something that's more related to a mathematical property called the Pigeonhole Principle. That's actually what's going on here. The Pigeonhole Principle is something which says if you have n pigeons, and they're all going into n-1 holes, well then some hole gets at least 2 pigeons. Basically, if you have more pigeons than holes, then your holes are not going to be enough. And what this is it's a bit of a generalization of that, where it's like I have all these holes, and each hole can hold up to 24 people. And the most people you can put in is 288. Okay, more questions. With that, hopefully we have some more questions which have come in. What else can we do here? Oh, and I see that some people were typing all of these answers in. Very nice. Luca asked, how are you doing? I'm doing great because you're here. Thanks for joining tonight. Okay, what else do we have? Oh, Sophia Tseng has a question. Based on the system given, what is the value of m plus a plus t plus h? Well, let's find out. So there's a system of equations now. I'm going to copy them down from, well, it's right in front of me on the YouTube screen. So I have m plus a equals t. That's one of the equations. Another equation is a plus t plus h. I'm trying to read this carefully because there are some spaces. I think your space means the next equation. A plus t plus h is equal to, wait a second. Now I'm confused. A plus t plus h. I'm wondering if there's a typo. So I'm going to ask Sophia then, could you please retype your question because a plus t plus h didn't have an equal sign following it. I do want to answer your question. Hopefully you're still here. So please type the new one in. Either that or maybe I just can't see. Let me try to look a little bit closer. M plus a equals t. A plus t plus h. Yeah, I don't actually have an equation there. It just says a plus t plus h. Oh, okay. Sophia Zheng says Jiang Michael answered it, which is great. Thanks, Jiang Michael, for being here. But I wanted to go and dig a little bit into this because I thought it was actually quite an interesting question. If I understand it correctly, I'm guessing you made a typo with the a plus t plus h. M plus a is t, a plus t is h. Oh, I get it. There's a pattern here. Oh, no, no, no. I see it. So you have a plus t equals h. You wrote a plus, but you meant an equal. I get it. It's just that they're going around, like m, a, t, h, and so on, right? I want to talk about this because this actually looks pretty interesting anyway. M, t, h, and t plus h is m, and h plus m is a. Okay? And you asked the question, what is m plus, yes, and thanks for writing that down, a plus t equals h. And what you asked is, well, what is m plus a plus t plus h? Okay, and I saw you said Jiang Michael already answered it, because somehow if you take all of these equations, you can do interesting things with them. But something I wanted to look at here is I was also kind of curious, how many solutions are there? Because, by the way, if you ask for m plus a plus t plus h, that's kind of weird. Why didn't you just ask me what m was? And the answer actually, I think, turns out to be that there's a lot of solutions. So if I look at these equations, for example, I see one solution right away. Oh, they could all be 0, right? If all of them are 0, then m plus a plus t plus h is 0. When I was doing math contests in middle school, somebody once told me, if the problem says find this, the answer is going to be a number. And if you can find any choices of numbers to put in to make the whole thing work, well then that's got to be the answer, because the answer can't be, I don't know. So actually, if I just know that 0, 0, 0, 0 all works, well then 0 has to work. And the answer actually has to be 0 from a contest perspective. Of course, I want to do math here, not just contests. But I wanted to point out that actually whenever you have some sequence of equations, a series of, what are they called? System of equations. If you have a system of equations and there are no constant terms, if there are no numbers there, like plus 5 or equals 17, then actually 0, 0, 0, 0 is always a solution, because you can just like put in 0 and adding zeros, multiplying by zeros, subtracting zeros, it's just 0. Okay, so that's actually how I knew the answer was going to be 0 even before I started, because I assumed you were giving me some math contesty problem and I didn't see any constants inside the equation. So I knew all of them could just be 0. But now, if you wanted to solve this properly, indeed, one thing you could do is you could add up all of the equations together. And if you added up all of the equations together, on the left-hand side, it's neat. You see, because you are going math all the way around. And so you're actually getting math all together. And in fact, m and m are here, a and a are here, t and t are here, and h are there. You got 2 of each. So actually, if you added them all together, I'm going to use this pink thing to explain what happens when you add them all together. Well, you get double of m plus a plus t plus h, and that's equal to just, m plus a plus t plus h again. So that means that this m plus a plus t plus h is some number where if I double it, I get myself. There's only one number in the world that does that, and that's 0. You can also see that by just subtracting an math, m plus a plus t plus h from both sides. That just gives you m plus a plus t plus h equals 0. So math equals nothing. Well, I guess that's just the problem. Math is not nothing. Math is actually more like 1 over 0 in the positive direction. Okay? So this is how you can solve this question to get 0. But there's something else interesting too. I just want to tell you, I think there's other solutions to this problem as well. That's my guess. And let's see if we can find out some other solutions to this question, this particular set of equations. Yeah, or am I saying yeah? Does it work? I'm just looking at this trying to think, can I go and try to make some other solutions to this set of 4 equations and 4 unknowns? Actually, maybe it doesn't. I'm actually using some linear algebra right now. I'm doing it in my head, so I could easily be wrong. But this particular set of equations, at first I thought, there might be other solutions too. But the only way to really know is to go and write it out properly. When I say write it out properly, I want to line things up. So I'm going to rewrite these equations. I just want to see what happens. I can say that I also have m plus a minus t equals 0. And I have a plus t minus h equals 0. And I have t plus h minus an m I'll put on this side equals 0. And I also have h plus m minus a equals 0. Okay, so now I've written out all these equations in this particular way. Okay, now there's something that you can do using systems of equations to try to figure out whether or not there are other solutions. That's actually an area of math that people often will start to learn in high school. It's where you use certain things called matrices. I'm just trying to think to myself if I want to go and teach this on this channel right now, only because I know that our age range is quite different. However, I can say that what you often try to do is you often try to clean up a system of equations like this to try to see if maybe, just maybe, it's something where we can solve and get precise values for all of these things. And one way that you clean these up is actually at first what you do is you try to get it so that your equations are such that you don't have any more m terms. You want to get from 4 equations with m's, a's, t's, and h's to only something like 3 equations where the 3 equations only have a's, t's, and h's. That actually has a name. That's called Gaussian elimination. But we can go ahead and do that by just using the top equation to clean up some of these other ones. For example, if I take this equation over here and I replace it with what I get when I add the first equation to it, if I add the first equation to it, let me draw an arrow the other way. I want an arrow in a way where I can I'm trying to be as not confusing as possible. So let me just draw the arrow this way. If I add the first equation to it, that's what you're able to do when you have equations, then I get a, the t and the minus t cancel, the m and the minus m cancel. I get a plus h equals 0. Wow, really? Did I make a mistake? I do that sometimes. I think I made a mistake. Yeah, I made a mistake because it's not a plus h. No, the h cancels with the minus h. Wrong, wrong. This is not. This is that I have the m's cancel, the m and the minus m cancels. I have, oh no, that was right. That was right. I was adding the first equation to this one. So the m and the minus m cancel. I have a 2t. No, sorry. The minus t and the t cancel. That's a 0. The a I keep and the h I keep. Okay, good. A plus h equals 0. I'll write it like this. A plus h equals 0. To me, that's suspicious. Okay, the reason that's suspicious is it only has 2 letters left in it. Let me try to do something with this equation too. If I take this equation here, and I take it, and let's see, I want to get rid of the m, so let's subtract. Let's take the first equation minus this equation. Or no, I should think of it this way. Take this equation and subtract the first equation from it. That's minus a minus another a is minus 2a. Now, if I subtract the first equation, I minus a minus t, so it's plus t. Okay. And then if I'm subtracting, I get to keep an h, so plus h equals to 0. I'm also just going to keep this a plus t minus h, just as it was, equals to 0. Okay? And so what I've just done here is I've just taken these 4 equations and 4 unknowns, and I used them to generate 3 equations and 3 unknowns. But the thing I'm finding quite interesting here is that I have a plus h equals 0. And that's where I was getting suspicious before. You see, because with a question like this, there's usually symmetry. If I could get that a plus h is 0, a and h are these 2. The way the equations have been written, it actually should be that I also can get m plus t equals 0. Is that true? I should be able to do a similar logic and get m plus t equals to 0, which would definitely give me that m plus a plus t plus h equals to 0. And then this is starting to tell me that I have certain things which are negatives of each other. A and h are negative. I'm trying to also see if I made a mistake here. So I'm just looking at this. Well, so far so good. So I've got this. Okay. Interesting. Interesting. I'm looking at this to try to see if there are other nice coincidences about this. But okay, let's just keep this. Okay, so I've gotten these. And the next thing I would do is I would just try to also, I've got 3 equations and 3 unknowns now. And with these 3 equations and 3 unknowns, I'm just trying to get rid of some of them So the way I'll do that is let's go from these last two equations and try to clean them up by getting rid of the a's. Now, in order to do that, I'll just replace this equation with this guy minus the previous one. And when I do that, when I subtract the previous one, I get negative t plus 2h is equal to 0. And then to clean up this one, I'll take this last equation and add 2 copies of the first one. That's how I'll cancel away the minus 2a with a plus 2a. And when I add 2 copies, then I get 3t. And h minus 2 of the h's, which is minus h, equals to 0. Okay. Well, in that case, now I have 2 equations and 2 unknowns. So if I've gotten that, now I just want to know whether or not I can clean that up. And the answer is yes, of course. I can actually do it by taking the third equation and add 3 times that previous one. And already what I'm seeing here is that, oh, good. So actually, it's very unique. The answers are, in fact, unique. So I take this equation, add 3 times the previous one. And when I do that, what you end up getting, let's just draw a little arrow this way. When you take this 3t minus h, add 2 copies of the previous one, the 3t minuses 3t, that gives you 0. Adding 3 copies of the previous one gives me a minus h plus 6h, so it's just 5 h's equals to 0. Boom! That tells me that h equals 0. So if I had any solutions at all, h has to be 0. Now you start backing it all out. If h had to be 0, now we substitute back into here. The fact that h had to be 0, so that's 0. So negative t plus 0 is 0. That forces t to be 0. Let's continue backing it out. Let's go over here. A plus h equals 0. Well, a plus 0 equals 0. So that means that a equals 0 too. I get that out of here now. A equals 0. And then when I go all the way back to here with the m, well, m plus 0 minus 0 equals 0. That tells me that m equals 0. Okay. So actually what I found out is that over here there's a unique solution. It's just 0, 0, 0, 0, and it just so happens to be m plus a plus t plus h equals 0. In high school, you'll learn something about determinants of matrices. So in fact, as I was doing this question, I was looking at it at first, I was wondering if there were multiple solutions for m, a, t, and h. And as I was looking at this, I was thinking to myself what that 4x4 matrix, that's what it's called, would look like. And then I suddenly was like, oh, actually there's a unique solution. That's kind of neat. And this is what we just saw here. Okay, more questions. What else is here? Yes, this live stream ends at 8:45. What else is here? Oh, lots of questions have been asked by now. That's terrific. And I'm just scrolling back to see this. Oh, Luca's here. Luca said, the guy from Brazil that took a picture with you when you were in a computer. Awesome. Okay, yes. I was in Brazil about a month ago. What else is here? Oh, come on. Abhijit Saha, how in the world do you know that question even exists? Something about the shortest number of jumps of length 5 required to get from 00 to 2021 if you're only allowed to jump to integer coordinates. That problem looks kind of familiar. And because of certain reasons, I will not want to talk about that this week because it looks kind of familiar. And of course, you know because you're asking me. But this is just because usually with exam problems, we talk about exam problems only when it's safely past the exam to explain why those are true. Okay, more things. People said m plus a plus t plus h is infinity. How nice. Okay. Okay. We probably have more questions by now. What else do we have? Oh, it's a puzzle. Let me try this. I always look at these and I like them because I have no idea whether I'll succeed, but they look kind of intriguing. So this is from Selena. Selena says you have an empty 3x3 grid. I'll start by drawing an empty 3x3 grid. I guess it's like tic-tac-toe. Okay. Who wants to play tic-tac-toe? It's not so much fun to play against myself. But that's okay because we're doing math. This says fill it with numbers so that the product of any row and any column is 1. Okay, so what do we need? You want to get product of every row to be 1. Okay, I hope this makes sense. I want that the numbers in the row multiply together to be 1. And also the product of every column is also equal to 1. And I also need that the product of any 2 by 2 square. So product of every 2 by 2 square, that's supposed to be 2. Ooh. And now the question says go and find a way to do this. Well, when I look at this, I'm first wondering how much freedom do I have? You know, I have 9 variables. I have 9 things that I can throw inside here. And if all I have to do is get products to be 1, that would be easy. Just make them all 1. But no. I have to make 2 by 2 squares give me 2. Okay, but how many rows are there? I'm just looking at how many constraints I have just to have a feeling of how safe this is. Like how much space I have to go and mess around with the numbers. Well, there are 3 rows. I'll call it 3 constraints, because each row has to multiply to be 1. That's constraining my choices. The columns, I also have 3 constraints. And the 2 by 2 squares, I'm going to guess that you're really referring to actual 2 by 2 squares. Like that's a 2 by 2 square, that's a 2 by 2 square, that's a 2 by 2 square, that's a 2 by 2 square. So 4 of them. Oh, yikes. Now this is challenging, because altogether the number of constraints I have is 10. And I have 9 variables that I can throw in. Oh, interesting. I see how one of yours is automatic from the others. So I initially get worried if I go and find out, oh no, I have more constraints than there are variables, because there's a general philosophy in a lot of these equations that if you have more constraints than variables, there might not be solutions. And over here, there's 10 constraints and only 9 variables. But the good thing is actually one of the column constraints is automatic. If I already knew that the product of every row is 1, then from the first 3 constraints, I also happen to already know that the product of everything is 1. Aha. Well, if the product of everything is 1, and you start telling me, well, these 3 multiply to 1, and those 3 multiply to 1, then you automatically know that those 3 also multiply to 1. So in fact, this row constraints and the column constraints altogether are actually only 5 constraints. So now it feels about right. It's like about 5 plus 4 constraints. Maybe there's some redundancy, but maybe not. But the bottom line is that over here, it looks like I might have just about the same number of constraints as I do variables, which means I have to be careful. Okay, well, if so, what else can I do? Okay, I was at first going to say, you know, we're doing products. I don't like products. I like sums. So what I should do is take the logarithm of everything. But that would be no fun, because logarithm of 2 is a mess. So we're not going to do that. Okay, so instead what I want to do is I want to think about, let's try this. Okay, I've got all these numbers. Let me actually label them with A up until whatever is the 9th letter of the alphabet. Anyone know what it is? I'm about to find out. A, B, C, D, E, F, G, H, I. Man, and I've just done 2 things that you should never do in math. You should never make a variable e, because e is 2.71828 and so on. And you should never make a variable I, because I is the square root of -1. But in this particular problem, we're going to go ahead and do these things, because we're going to hope that complex numbers aren't required for the solution, and e won't be in there, almost definitely. Okay, so now that I have all of these, I want to think about what might happen if I try to combine these constraints in some other way. So for example, the 2 by 2 squares, they multiply to 2. So I wonder what would happen if I just, for fun, just started multiplying them all together. Excuse me. Oh. One of the benefits of stopping to drink water is that you might just start to think about something. So what I started thinking about, and don't worry, I don't have some kind of a disease. I don't know, something just got into my throat. But now here's something I'm seeing too. Because what I'm trying to do is I'm trying to like paint over all of this square with some numbers. What do I mean? Well, I actually already know from the first thing. Product of the first 3 is 1. Product of these 3 is 1. Product of those 3 is 1. So the product of everything is just 1 times 1 times 1, which is 1. So I already know that the product of everything is equal to 1. Okay, but now what I'm going to do is I'm going to go and choose a 2 by 2 square. Let's highlight it. That would be fun. So let's highlight a 2 by 2 square over here. That multiplies to 2. And let's go and highlight this particular row. That multiplies to 1. And let's also highlight another row. Actually, column. This is a column. I'll highlight this column. That multiplies to 1 also. Now here's what I want you to see. You see, this thing got hit twice. So what did I actually achieve? If I multiply together that square and that row and that column, I've actually multiplied everything in the entire 3 by 3 square, but I in fact multiplied the a twice. That's a squared. So if I multiply all those things together, well, what do I know? I know that the product is equal to 2 for the 2 by 2 square times 1 for that row across the top times 1 for this column down here. And what that's equal to is it's actually multiplying everything in the square all together, but also multiplying by a again. So this is equal to product of everything, because I use everything once, and then times the a again. Oh, well, what does that tell me about a? That just tells me that a equals 2, because the product of everything is 1, right? Product of everything is 1. So 2 equals 1 times a. That means that a equals 2. That was somehow very satisfying. Like, I didn't have to write down lots and lots of equations, and I'm already able to use this information to say, oh, that one's 2, that corner there is 2. But by symmetry, boom, you're going to be able to get all of the other corners to be 2 as well. Oh, thanks for making the comment. Nice joining this live stream. Well, nice to have you here joining this live stream. Welcome. But now let's go and use what we've just learned. Because of this, I now know that by symmetry, I can use the exact same logic. I really like this question. Thanks for sharing it. This question here. Now I know for sure that each of the corners is 2. Okay? And that has to be because, well, if one of them is 2, then all of them are. The same logic would just work. Now let's start using the fact that the product of every row is 1. If the product of every row is 1, then I know that 2 times something times 2 is 1. That means that's a quarter in there. And this is also a quarter. And this is also a quarter. And this is also a quarter. Okay. Oh, I'm glad that you like this concept. I like having you here too. Let's finish up. Because now if I need the product of the row to be 1, then that means that a quarter times this has to be 1. Then that has to be 16. Does this actually work? Whenever I fill out all the numbers, I want to just double check. Is this actually satisfying everything that I started with? Because you see, when you're solving equations, actually logically what's going on is you're just making deductions that say, if there was a solution, the solution would have to look like this. But nowhere do we know that it's definitely a solution until you actually are at the end and you go and check it to see if it works. In most of the math problems you get in school or in math contests, of course it's going to work because they asked you to find the answer. But if you have a mathematician looking, the mathematician wants to just make sure it worked. So let's look. Is the product of every row 1? That makes 1, that makes 1, that makes 1. How about the columns? Well, mathematicians are also very lazy. I'll use symmetry and say, well, the columns will be the same thing as the rows because the whole thing is symmetrical. Symmetrical, I'm actually talking about with the idea that you swap the rows and the columns. And now how about the 2 by 2 squares? By symmetry, they're all the same. Let's check this one. 2 times half times 16. No, not half. 2 times a quarter times 16. Oh, yes, it works. Because the quarter, and the 16 cancel. And what's left is 2. It works. So, nice. Thanks very much for sharing this question. It turns out that I didn't even need to write my variables. It turns out that if you wrote the variables and tried to solve it, you'd probably get a mess. But with these kinds of problems, sometimes by using this logic of what I call painting the square, it actually ends up being much nicer. Okay. What else do we have here? Yes, Luca, you're right. You really need to see if they really work, just like in all functional equations. That's a topic that often comes up in high school mathematical Olympiads when people have to go and write proofs that go and explain why things are true. And on the International Math Olympiad, if you have what's called a functional equation, where it asks you, what are all the functions that satisfy something? if you don't check it, you actually usually lose 1 point. So always do this last step. Maybe that's why I'm doing it, because I have the habit of, after you get all the way down here, just make sure it actually works. All right. Cookies. What is this? A cookie problem. If Cookie Monster has 6 ovens, each baking 6 batches of cookies every day, how long will it take Cookie Monster to bake 6 million batches of cookies? Okay. 6 ovens, each baking 6 batches of cookies every day. Well, it looks like Cookie Monster gets to keep using all 6 ovens. All right. So in that case, you know, the 6 ovens each bake 6 batches of cookies every day. Okay. So in that case, if Cookie Monster wants to bake 6 million batches of cookies, well, let's put it this way. If I had 1 oven baking 6 batches of cookies every day, then to bake 6 million batches of cookies, I need 1 million days. And so if I have 6 ovens, I just divide by 6 because I get to go 6 times faster. So it's 1 million divided by 6. I'm doing it in my head. That's like 1,666, a bunch of 6s. And so that's going to be 166,666 days and 2/3. That's actually how long it will take. I think what that means is that Cookie Monster will probably not be around anymore. Yes, the ovens will be destroyed by then. Lucas says more than 3 hours. Oh no! A Bush says, however, Cookie Monster eats 1 batch every day. That's hilarious. You guys are great. These are like these other problems where you make progress and you take away progress at the same time. But I should also say, this thing about like 166,000 years, here's a really interesting concept that I've thought about sometimes, which is like, you know, if human beings just suddenly vanished, not vanished, sorry, if somehow all the humans died tomorrow, maybe due to some horrible virus, what would the world look like in 1 year, in 10 years, in 100 years, in 1,000 years? If you think about this, it's actually pretty interesting because all kinds of things start to corrode and turn to dust. And somebody was saying the ovens wouldn't exist in 166,666 years. That's true. Like that far in the future, all kinds of things just disintegrate. Which sometimes makes you wonder, could there actually have been another civilization on Earth somewhere that just blew itself up, like, I don't know, 300 million years ago? That's a long time. Who knows? These are deep thoughts. Anyway. Oh no, some horrible virus. Yes. Well, hopefully not this one. Okay. More questions. Yeah, then the new species like the dinosaurs. How do you know dinosaurs didn't have airplanes? Maybe they had airplanes, and just like all the airplanes corroded, like, you know, about 5 million years after they died. In some sense, the things that would last the longest are if they had like radioactivity. So I think we're fairly confident that the dinosaurs did not have nuclear reactors because we would have seen the pileup of all of the spent nuclear fuel. But like these are sometimes like interesting thoughts. It's like, how long does everything last, right? Like if dinos had cars, how would you know? Well, okay, maybe some things would have lasted. Maybe we would have found like some metal in some shape. Who knows? All right, maybe all the airplanes blew into space. Well, we are obviously having some fun with this live stream. What else can we talk about? Oh, okay. Somebody asked me a question that's a little bit more about like more advanced math. So I'm just going to say, I'm going to pass on this one. I'm trying to make this live stream as welcoming as possible to people who are new to this space. And so you're asking, Frederick Weaver asked me a question about polynomials and and composite integers. But I'm just going to say the level of this live stream, we're aiming to be one that brings as many people into this subject as possible. So I try to be careful not to go with things too deep. So Jiang Michael says, prove that the sum of the angles of a triangle in the Euclidean plane is 180. Okay, so yes, Frederick, yes, that's right. So like back to Jiang Michael's question, the sum of the angles of a triangle in the Euclidean plane, this actually depends on how you axiomatize geometry. But the way I often explain this to people who are looking at this sort of thing for the first time is I say, oops, I already drew an extra line. Let's not do that yet. Here's a triangle. Hooray! And once you have this triangle, then there are certain principles that you use. You just kind of draw this thing over here. And when you draw this thing over here, then what you do is you say, well, I have these parallel lines. It was supposed to look parallel to the bottom line. Let's try again. Maybe that's better. You were supposed to have these 2 parallel lines, right? This is just draw a parallel line, which, by the way, is a non-trivial thing to do in what's called non-Euclidean geometry. But what he said is Euclidean. That just means this flat plane. We have something called the parallel postulate, which says that if I have a point and if I have a line, there's exactly one line that I can draw that's parallel to this one. Okay? But when you're in that space, well, then you have what are called alternate interior angles. Those two are the same. And I also have alternate interior angles over here. These two are the same. And now this angle just sits here. So now if I go and add the three angles together, that's the same as these three angles together, which is 180 degrees, because that's just going halfway around the circle. So at that point, if I went halfway around the circle, that's going to be 180. By the way, if you're curious, why is it that we have 360 degrees in a circle? Well, that's a really interesting question, because why should you? You could just have said, like, I make circles to be 100 degrees, like percents. But there are some pretty good reasons why 360 degrees were chosen by ancient humans. One of them was because it's nice to divide 360 by things. Like, I don't like taking 100% and dividing it by 6. That's 16.6666%. Not nice. But if I took 360 degrees, I can divide by 6, no problem. That's one reason. But there's another reason, which is actually even deeper. Not deeper, even bigger of a coincidence. The bigger coincidence is that it's because the number of days in a year is pretty close to 360. So in fact, if you were looking at like the positions of various other stars or planets or whatnot, and you were having things going around, you would actually be able to notice that somehow, almost like every day, it would move 1 degree, something like this. So it turns out that this 365 days in a year, 365.25, or if you're more careful, like even more careful corrections, this approximately 360 days in a year influenced ancient human civilization's choice of 360 as a nice way to measure these orientations. I myself am actually not an expert at celestial navigation, so I'm way out of my depth here. But I remember reading that people could do interesting things with looking at directions of various galaxies, and ancient civilizations were able to start thinking about like a day being moving just by one of these ticks on this protractor. Okay, more questions here. What else do we have? There was somebody who also asked me a question about the triangle inequality in non-Euclidean spaces. The triangle inequality just means that, actually the triangle inequality just says the shortest path between 2 points is a straight line. And that's even if you happen to be in what's called non-Euclidean space. Non-Euclidean space might be if I just took the surface of the Earth. Let's pretend that this lump is the Earth. Sort of okay. So this is the Earth. And if I have the Earth, well, it turns out that if I'm going to fly airplanes, and if I want to fly, from here, and I want to fly over to there, and then after that I decided, let's just go fly over to here on the equator to hang out because it's maybe better weather over there, then if you fly, it's actually pretty interesting. What that looks like on the Earth is it's not a straight line. A straight line on the Earth is not a way to fly. That's called having your plane crash very badly as it goes straight through the Earth, which it can't do. So you have to go on the surface, right? So as the Earth has eyes. Oh, you guys are hilarious. So I mean, what you actually have here is that you're kind of flying over on the Earth, and then you're just going to fly south, okay? So, by the way, these are supposed to be the shortest paths between these two different... Oh, you guys are great. The Earth is smiling. It almost looked like the Earth was taking its temperature. That's what I thought as soon as you said it had eyes. This is like a thermometer or something. But anyway, the triangle inequality says that if I wanted to go from here, fly over to there, and then fly over to there, even if I went in the shortest possible route on each of those, that's still going to be more jet fuel. Shouldn't say jet fuel. That's going to be more distance than going straight line. Okay, and that actually works even on non-Euclidean surfaces, things that aren't flat. You noticed I caught myself when I said jet fuel, because actually that's not the right thing. There are ways, in fact, to move from one place to another place without even using any jet fuel at all. That's by using something called the jet stream, which is just flying around in the atmosphere. Okay, more things. Oh man. Okay, somebody said that you watched a video where I talked about Euler's identity. Could I explain how all of these weird irrational numbers equal -1? That actually is the topic of a talk that I give for about 1.5 hours. So I will never be able to put that right in this live stream. I wonder if it's on YouTube somewhere. I did give it somewhere. Somebody recorded it. So I'll just say that's that's too deep for what I want to do in this live stream. We have only 1 minute left. Let's just do some quick things now. Let's see. the triangle inequality, which was that the sum of any two sides of a triangle must be less than the third side. I think, I'm not exactly sure. No, the sum of any two sides of a triangle must be less than the third side. That triangle inequality. Actually, it's the other way. Sum of any two sides of a triangle is more than or equal to the third side, and that's the same here, because actually, same concept. Because if I have the sum of the two, actually it goes this way. If I have the sum of the two sides of this, it's always going to be bigger or equal to the third side, because the shortest path between 2 points is always going to be going direct instead of trying to go via a detour. No problem. Okay, but with that, unfortunately, we have just gotten to the end of the time. Somebody just asked me how you distribute time for math counts, better than what I'm doing right here, where I'm just doing interesting problems. Quick answer to your question. The answer is, I guess if you look at a problem, hopefully you can practice enough so that you're able to do most of the questions. And then how I would distribute the time is just really try to do them, because if I skip over a problem, then unfortunately I've spent all the time to understand the problem, and I'm still not doing it. So my answer there is just learn as much math as you can. Think about as many hard problems as you can, so that math counts become something where you actually can solve the problems. And then the way you do it is you go straight on through. And only in certain cases you skip a problem when you think you really don't know. It's just because from my experience in life, oftentimes as you're working on a question and you're not making progress, you actually are. There are very few things that are so hard that you really can't bust through. And so to me, it's like if you've invested the time to think about it, crash it all the way through. With that, we're going to call it a week here. Next weekend, I'm actually not going to be running a live stream, primarily because I will be in San Francisco. I'm actually giving the colloquium talk, the final talk this year for the Berkeley Math Circle. So I'll be at Berkeley next week, Sunday. But the following weekend after that, I'll be back. So I'll see you guys in 2 weeks. Take care. Bye-bye.